Alright, hey guys, it's Miss Scott coming to you from in front of my whiteboard. I was asked if we had a video on the atomic families, and now we do. So here we go. Alright, what I will be conveying in this video, I will be talking about the characteristics of the atomic families, their valence electrons, the charges they typically are when they're ions, and some other fun characteristics on how reactive they are, etc. Bohr diagrams and Lewis structures for each. Alright, so we'll go ahead and start. Before we begin, I want to make sure you know a couple of vocab words. A group on the periodic table. When I say, elements are in a certain group, that just means they're in one column. And this is part of the beauty of the periodic table, is that they have managed that through its development, we've managed to put elements that all act like one another, that look like one another chemically, into one group, into a single column. As this table was being developed, obviously we didn't know all the elements yet. We haven't discovered them all. So there were gaps, but as we discovered them, they ended up fitting where these gaps were based on these patterns, which is part of the elegance of the periodic table. All right. Another thing you should know, you should be familiar with, before we talk about the individual groups, are the big subcategories that are on the periodic table. We have the metals and the nonmetals. The metals are on the left, so from the transition metals over, if you have your own reference table, there a lot of them are color coordinated to help you find each of those, like this one here. In this particular book, the metals are in blue and the nonmetals are in orange. These in green here are metalloids. They're not quite metals, they're not quite nonmetals. They're generally solids at room temperature, but they don't quite act like these, so they're kind of in their own little category. All right. The only nonmetal, the only exception to this metal-nonmetal rule is hydrogen. He is a nonmetal, but he is placed over with the metals, and we'll talk about that why in just a second. All right. So let's go ahead and start with the families. I won't go into detail with every single family. There's a couple that I want you to know a little bit more about than others. For all of them, I want you to know how many valence electrons there are, the Lewis structures for each. But we'll get there. I'll get there. All right. So our first group, we'll start left to right. So we'll start at the far left, the metals. This is the alkaline metals. They are metals. Again, the only one that's not a true metal that's in this group, and the only kind of one exception to this rule, is hydrogen. Hydrogen is a nonmetal. I hope you know that. Hydrogen is a gas at room temperature. But the reason we put it over here is that alkali metals have one valence electron. And what a valence electron is, remember, that is the electron that's on the very outer shell of it. So this is lithium. Remember, lithium has 3 electrons in its neutral state. It doesn't like to be in that state, by the way. I put 2 on the first row. I can't fit any more, so I move up a level, and there's 1. Hydrogen, even though it's a nonmetal, hydrogen only has 1 electron in its neutral state, so it has 1 shell and 1 electron. So really, if you take out that middle, these two look the same, so they act the same. All right? We talked about the valence electrons. They determine how the atom reacts with others. Hydrogen and all the alkali metals, really, lithium, sodium, francium, cesium, what else? Rubidium, potassium. They only have 1 valence electron. This is not a stable state for it. In order for it to be stable, the outer shell has to be full. Well, in order for it to be full, it would have to pick up at least 7 more if it's on that second level. So it would be much easier for it just to get rid of 1 electron, which is what it does. So every alkali metal will always have a charge of positive 1 when it becomes an ion. That makes the alkali metals very reactive. You can look up a bunch of YouTube videos showing you what happens when you put pure sodium or pure potassium in water. It's a great reaction. It's very violent. It happens very quickly. You see a lot of energy being expended. So fun stuff. Very, very reactive because it's very close to being stable, but not quite there. All right, the alkaline earth metals. So we move over one, the alkaline, now we go alkaline earth. They sound the same, but they're a little different. They have 2 valence electrons. So if you want a diagram, a Lewis structure of that, you would have the element name, like beryllium. It's got 2 dots. All right. Because it has 2, it's going to lose those 2 in order to become stable instead of gaining 6. Remember, to be stable, you want 8. That's where I'm getting these numbers from, by the way. They will always have a charge of positive 2. In terms of reactivity, they're less reactive than the alkali. It takes a little bit more energy for them to become stable, so they're not so... They will react, but not quite as quickly as the alkaline metals, not in the same fashion. All right, so you can mix calcium and water and you'll get a little reaction, but not like if you did with sodium. By the way, don't put sodium in water. Don't try that at home. Don't. All right, our next group we'll talk about are the transition metals. This spans from group 3 to 12. This is not to scale, obviously. The transition metals are what you probably think about when we think of metals. Iron, cobalt, nickel, gold, silver, zinc. Zinc's another one. The transition metals, what I want you to know about, what I want my kids to know about them, they have varied numbers of valence electrons. So we can't really make a good Lewis structure to encompass all of them because they all can be different. Iron can have a charge of +2 or +3. So we don't get into that in our particular course, but if you need to, seek your instructor for that. They are metals. Because they're metals, they are going to lose electrons and become positively charged. And they are less reactive than the alkaline metals, the alkaline earth metals. So we know things like iron, if you leave a piece of iron out into the elements, no pun intended, if you leave a bar of iron out somewhere, it will rust. That's a reaction happening. But it's not a very quick reaction. It's not a reaction that occurs spontaneously necessarily. It takes a lot for these to react with other things. They are able to react, but not to the capacity of these. This will always, always, always react the second you introduce it to something else. These, not so much. They are a bit more stable, but not totally. All right, the next families, I'm only going to go over the valence electrons for these. B stands for boron, C stands for carbon, nitrogen, and oxygen. This is the boron family, carbon family, nitrogen, and oxygen. They're not very uniquely named. They do have other names. We don't go over that. But what I want you to know is the trend, and we talked about this trend when previously. Boron, things in the boron family, that would be like aluminum. They have 3 valence electrons. Their Lewis structures look like that. The carbon family, they have 4 valence electrons. They'll have 4 dots around their Lewis structures. So boron, aluminum, all of that would have 3 valence electrons. Carbon, silicon, germanium would have 4 valence electrons. Nitrogen, 5 valence electrons. Hopefully you see a pattern by now. The oxygen family has 6. 1, 2, 3, 4, 5, 6. And as you go up in the number of valence electrons, now it starts becoming easier to pick up electrons than it is to give all of them away. So boron, in the boron family, 3 is a smaller number than 5, so your charge will be +3. It will lose 3 and have 3 more protons. Carbon is kind of weird. These are typically more involved with covalent bonding as opposed to ionic. It likes to share electrons with everybody else as opposed to either getting rid of them or taking them. But if it were to become charged, it could either lose electrons or gain, and that's going to depend on the element that the other element that it's interacting with. If that element is more likely to take or lose that will determine what carbon does. Nitrogen, now I have 5. Now it's easier for me to gain. Gaining 3 is easier than losing 5. Charge of -3. Oxygen has 6. Everybody in the oxygen family has 6. It's easier to gain 2 than it is to lose 6. So charge -2. Halogens, now we're going back to our named families that I care about. The halogens are really fun. Halogens have a neat naming system. All halogens end with I-N-E. So we have fluorine, chlorine, bromine, iodine, and astatine. So just a fun. So if we found another one, we would probably give it that name. Probably. I'd hope we would. All right. So the halogens. So I will use F as they have 7 valence electrons. So 7 on the very outside. So 1, 2, 3, 4, 5, 6, 7. Remember, in order to be stable, I need to get to 8. So now, if you follow this trend, you follow the pattern, I know that fluorine is going to just pick one up. It's just going to pick one up to make 8, which would give it a charge of -1. It would be very easy. So think back to when we talked about the alkaline metals. The alkalis, they only need to lose 1. That doesn't take a whole lot of energy, so that reaction will happen very quickly. Halogens, it's like the same. It's the other side of the same coin. I only need to pick up 1. That doesn't take a whole lot of energy. Fluorine, things like fluorine, chlorine, bromine react very quickly. They are the most reactive of the nonmetals. So the alkali are the most reactive metals, halogens, most reactive nonmetals. All right. And last but most certainly not least are our dear friend, the noble gases. There's a reason they're named the noble gases. If we think back to history, way back in the day, and you think of nobility, typically when we think of nobility, we think of individuals, locked away in the ivory tower or whatever, and they don't interact with the commoners or the peasants or whatever. Noble gases, you can think of that as the same way. Noble gases are totally and completely unreactive. They don't react with anybody. They don't. And you might be thinking, well, why? Why are they too good for you? Why? That's a great question. You look at their valence electrons. So noble gases, with the exception of helium, noble gases have 8 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8. So everybody else on the periodic table, they've been fighting to either gain electrons or lose electrons in order to get to this magic number 8. 8 valence electrons on the outside. Neon and all the other noble gases are already there. So if you already have 8 valence electrons, why would you waste energy picking up electrons or getting rid of them? You don't need to. Helium is the only exception. But if we look at helium is kind of up there on that first row, kind of by itself, on the same level as hydrogen. It has only one valence shell. It has only one shell of electrons. And we know on the first shell, I can only have up to 2. So the Bohr diagram for helium looks like this. 2 valence electrons. But it has only one shell to start with. So it is already full. So it acts the same way. It has the right number of valence electrons. It's happy the way it is. All right? So that is the periodic table. The families I want you to know, their respective charges, the respective charges for noble gases, because they don't react with anybody, they don't change the number of protons, they don't change the number of electrons. Their electrons and protons are always the same. They will always have a charge of 0. They don't become ions. They're happy the way they are. All right. So that is the periodic table and the families in a nutshell. If you have questions about any of them, please feel free to comment, and I will get back to you as soon as I can.